Hello, my name is John Ryu, and this is my presentation on the combustion dynamics in the Rijke tube. Rijke tube is essentially a pulse combustor, which is characterized by the acoustic oscillations inside the tube. The tube acts like an organ pipe, essentially, with the acoustic waves inside the tube creating resonance, which can be observed audibly. These these oscillations, acoustic oscillations, are occurred by the pressure, velocity, and heat fluctuations that occur inside the Rijke tube. These three properties are essentially coupled to each other, which means that these fluctuations in pressure, velocity, and heat fluctuations essentially drive up the oscillations or acoustic waves inside the tube. This is also known as acoustic driving. This occurs until the acoustic loss inside the tube equals to that of the increase of the acoustic waves. The experimental setup used inside the experiment is shown here. The Rijke tube the experiment was done inside the basement of the Engineering Science Mechanics building here at Georgia Tech. 3 pressure transducers were equipped on the Rijke tube, equidistant from each other, as well as a photomultiplier. The Rijke tube was also equipped with a valve that could be used to expose the flame inside the tube to atmospheric pressure. The burner plate could also be elevated up or down to position the flame inside the Rijke tube. This was used inside the experiment to observe how the position of the flame affected the acoustic waves inside the tube. 3 different conditions or positions of the burner plate was observed. One at its original position, marked as 0 inches, 2 at around 2.5 inches, and 1 at 5 in the last position at 5.25 inches. In addition, one case where the burner plate was located at 0, the valve was also opened. The following raw data shows the data values that were calculated, or the data values that were observed by the pressure transducers and the photomultiplier. The RMS voltage, peak frequency, and the associated phase was used or recorded by the pressure transducers. They were recorded at both the 0 inches, 2 and 5 inch positions, as well as the 0 inch position where the valve was opened. Before any data reduction could be done, the sensitivity of the transducers had to be known, and this was provided to us by the transducer calibration data. The sensitivity value was 96.8 millivolts per psi, which could be used to basically divide the RMS voltage in volts by the sensitivity to achieve the RMS pressure values in pounds per square inches. The pressure values were converted to sound decibel value pressure values by taking the base log 10 of the ratio of the pressure RMS value with the human hearing threshold pressure value, multiplying that value by 20. Also, the resonance frequency was estimated of the tube by dividing the speed of sound, A, by the wavelength, which is 2 times the length of the tube, which is twice the length because only half of the standing wave occupies the length of the tube. The first experiment, where the burner plate was located at its original position with the valve closed, observed a turbulent flame with very high resonance. This makes sense since the peak frequency observed was 96 Hz, where the estimated tube frequencies were 94 Hz. Since they were very close, it makes sense that there was high resonance inside the tube. The next experiment, where the valve was opened, the flame was still turbulent, but there was very little resonance. This makes sense since the peak frequency observed was only 1 Hz, whereas the estimated resonance frequency was 94 Hz. The next experiment, where the plate was elevated to 2 inches, with the valve being closed, the flame was still turbulent, but there was also a lot of resonance, just like the 0 inch position, or the case where the plate was at the 0 inch position. And this is also shown from the peak frequency, where the peak frequencies was 96 Hz, and the resonance frequency estimated resonance frequency was 94 Hz. The next and final experiment was when the plate was elevated to 5.25 inches with a closed valve. The flame was much more laminar and experienced very little to no resonance. And this is shown by the data where the peak frequency is only 1 Hz, and the estimated tube resonance frequency was 94 Hz. Here also shown is the relative phase angles at the 0 inch position. This was calculated by dividing, or by subtracting, the pressure transducers at the top and the bottom and the photomultiplier with the pressure transducer value in the middle, position in the middle of the tube. Finally, the conclusions made in the experiment first to apply to many propulsion applications. One conclusion made was that the position of the flame affected how laminar or turbulent the flame could be. In the propulsion application sense, this would affect the stability of the flame. Where the flame would be positioned would increase or decrease the stability of the flame, which could be significant in the propulsion application. In addition, the mixing itself in a pulse combustor can be observed to be very efficient, which in a propulsion application is very beneficial. As the acoustic waves drive better mixing, pulse combustors can be used in a case where mixing is very important. In addition, the standing wave observed inside the tube was also very significant, as it showed an acoustic phenomena as well as how pressure fluctuations affected the acoustic vibrations and acoustic fluctuations inside the tube itself.